on multiple linear regression in SPSS. And there are, of course, multiple ways of doing this, and you can call it multiple things. The first way that we're going to run this, you might actually call an analysis of covariance, but I promise you it's the exact same thing as multiple linear regression. Now you'll need to use linear regression whenever you have one or more continuous independent variables. You can still have as many categorical variables as you want, but once we get into the continuous realm with one or more of those independent variables, then regression is what we should use here. Okay, so let's head on over to our class website. We're still in week 3 here. We're now in our multiple regression tutorial. There's still an SPSS checklist that you should use, and the practice data sets here. We're going to use 2 for this video. We're going to stick with our pre-post, which we used in the repeated measures ANOVA video. We'll also run into this stepwise so we can see how you can build more complicated regression equations. So back in pre-post, this is still in SPSS from our last video, and this was analyzed before using a repeated measures analysis of variance. The problem that we came up with is that we didn't know how much more one group improved than another. So a better analysis would be clicking on univariate here, and what we're going to now do is, well, heck, this is already made. I'm going to make sure that let me clear everything out. My dependent variable would be the post or the follow-up scores. So what do they look like in the end? And I want to separate it by group. That's my fixed factor here. So I assume the effective group is consistent. And my covariate is their baseline score. So that's why you could also call this an ANOVA. I promise you it's the same thing as regression, and I'll show you in just a little bit. Alrighty, so what are we going to look for here? Really, same thing as last time, so hopefully this is all good. We're not going to look for any kind of interaction plot here. We're not after that. What we care about here is the EM means just for the group. We want to compare the main effects, and again, this won't make a bit of difference, but I'm just going to get in the habit of pressing Bonferroni in case there are more than 2 groups. There aren't. We have control and intervention. I can ask this to save my unstandardized residuals so I can check that again. I've done this before, so I'm not too worried about it. I'll leave it checked. Right? We checked all of our assumptions last time. And so we'll click OK here. And you'll notice this looks very similar as last time. Here's our test now showing us we've got a main effect of group here, right? So there's a difference between the groups after we account for baseline scores. Okay, so here's the whole interesting part of this down here. Finally, we've got our estimates and we've got our pairwise comparison. So this is what we think the follow-up scores are on average for the intervention group and the control group after controlling for baseline scores. So they just plug this value into the regression equation, and that spits out the estimated marginal means. What we're finally after here, the last piece of evidence that we wanted to report from our repeated measures ANOVA is this, the confidence interval for the between group difference. How nice. Now, this is the same thing as regression, and let's see if we can get the same thing. So we're going from about a 4.3 to a 13.1 point difference in terms of change scores. Okay, another way we can get this is with the actual regression dialogues. But before we can do that, we have to change this group variable because regression is not going to allow us to put in string in SPSS. So we have to transform, and I'll just keep it as the same variable, this group. And I have to take, if it was control, I got to turn it into a number. I'll call it 0. And if it's intervention, I'm going to call that 1. I'll say OK. And now I've got 0s and 1s, but notice it's still string. So I'll go down to variable view, and I'll lie to it and say, no, these are numbers. And now the regression function is going to be happy with me, I assume. Let's see. So we go to Analyze, Regression, Linear. We click on this, and we're greeted with this, which looks very similar to our last dialog box. So the dependent variable is still post. My independent variables are still pre and group. Now I could do multiple rounds of regression if I was trying to figure out from a big bunch of variables which ones matter for predicting my outcome. I would do that. I'm not interested in that. The whole reason that I'm running this regression analysis is to make sure that I can estimate the difference in change scores. I'm not actually trying to predict anything. As far as statistics go, we want our estimates. We definitely want 95% confidence intervals. Model fit is great. R-squared change, I'm going to check because I know I'll need it later. I don't need it right now. I don't care much about descriptives. It's nice to get the collinearity diagnostics. That's good. And we want this Durbin-Watson analysis of the residuals. So we'll click OK. As far as plots go, we still want to look at the residuals on the y-axis as a function of the predicted values. Hopefully what we'll see here is that we have about as much over and underestimation, that is, the residuals are positive and negative, with the low predicted values and the high predicted values. Histograms, normal probability plots, PP plots, these are great. We're going to check those, and we'll say continue. From here, we're going to click OK. I already have my residuals saved from earlier. Let me see if we're still doing that. Okay, good. If I didn't, I might save those just to check them out. Okay, and now I've got my regression output. Here, this is telling me my model summary. The Durbin-Watson statistic is there to talk about independence of errors. So hopefully there's no autocorrelation, so correlation between different subjects or anything. No, everything looks fine. This is about 2. If it's below 1 or above 3, I'll worry, and I'll look more into that. But we seem fine here. It's between 1 and 3. This is showing me my R-squared and my adjusted R-squared. So time and so baseline scores and group are explaining about 66% of the variability in follow-up scores. This is indeed a significant model. We can see it over here. We also see it down here. Exact same thing, right? We go down to coefficients. Pre, for every point in baseline score that we had, that gave us about 0.88 points in the follow-up. So it's almost 1-to-1. Hey, 1 is in my confidence interval, so we could say it's about a 1-to-1 relationship. And what does group do for me? Well, if I'm in the intervention group, that would be the value 1 in this case, I'm about 8.7 points higher. Let's scroll back up here. Oh, here we go. Sorry. Our pairwise comparisons from our ANOVA. Hey, 8.7. Look at that. These match. Of course they do. It's the same thing. Confidence intervals. 4.343 to 13.109. Exact same thing. So you can use regression. You can use the univariate ANOVA. That's totally fine. It's your choice. If you're going to use regression, you just have to make sure you dummy code those variables and make sure they turn into numbers. We'll go through another data set now, run this regression again to see how we can do more complicated analyses. So let me clear out my window here, and we'll get rid of these data. For this, let's go to our stepwise data set, and I'm going to go ahead and just take all of this. I'll copy it. You can see we have 49 data points here. We'll put those in. And now I just need to do a little bit of legwork. So the first variable here is what group are they in. Second variable is going to be their age. There we go. Sex, then we get BMI, then we'll have current pain, and current injury. You can call these something shorter if you like, CP, CI, doesn't matter, as long as you know what it is. The next three variables are previous injury, previous surgery, and then some kind of concussion. Shoot. Previous injury, and this is the hard part, just typing. Previous surgery, concussion. And then we have our baseline, I'll call it pre, and our follow-up, I'll call it post. All right, everything looks okay until we get to our measure column. I just need to say these are scale. It wasn't sure. So now we're all happy. Everything is labeled. Hopefully you're up to here. We go back, and now we're greeted with this. Now you'll notice we've got a lot of variables that aren't numbers. For example, group. I got to fix that. So I'm going to transform, and I'll recode it into the same variable. Let's go with group. Oh, we were close. It's too bad. Wasn't capitalized. So control with capital C, will be 0. And intervention with a capital I, it's going to be 1. I'll click continue. We'll say OK. And look at that. I got 1s and 0s. How nice. Sex. F's and M's. I got to fix that one too. So we'll transform, recode into same variables. We'll get group out of the way, and we'll throw sex in there. Let's make our males the 1. This doesn't matter. You just have to remember which one you made which, because now the effect of sex in our regression model is going to be the effect of being male. And we'll say OK. It's all fine. It sees the length of some variable, shorter variables, padded with blanks. I don't know what it's so upset about. Everything looks fine to me. Yeah, I don't know what it's talking about. It's all 1s and 0s. Oh well. Sometimes SPSS just needs to vent, I suppose. Okay, so we'll pretend like that didn't happen, and we'll transform, recode into same variables, and now we can finally do this a little more efficiently. All of these values, my current pain, injury, previous injury, surgery, and concussion, all are either yes or no, and yes is always bad. So I'll take yes and turn it into a 1. And we'll take a no and turn it into a 0. I'll click continue and OK, and hopefully everything's right with the world. And yeah, this all looks fine. For some reason, SPSS is still unhappy, and you know what? So am I too. Okay. Variable view. Now I need to lie to it. Group used to be string. Now I turn it into a number. I'll click the ... click numeric, and say OK. And we'll just tell it a little old white lie. And I'll just copy and paste that on the rest of my variables. And now we're all happy. I don't care if this says scale. Doesn't matter. It's a lie. Here. Let's lie about them all. There we go. And now SPSS is going to let me run my regression here. So I got a lot of possible variables that might matter. Are you currently in pain? Are you currently injured? Right? These scores that we're looking at are measures of well-being. It's measured on a scale 0 to 100. Have you been injured in the past? Have you had surgery in the past? This could affect your improvement. Do you have some concussion or balance issue? I don't think sex will matter, but hey, you never know. So there's a lot of variables that I think might explain this change from baseline to follow-up. So I can, if I really wanted to predict follow-up, I could put all those variables in and see which ones matter. So first let's run this in a way that I don't really care to do right now, but maybe you will. So we'll go analyze regression linear. We're going to run a linear regression analysis just like last time, and we got junk in here from before. Get out of there. All right, my dependent variable is post. And I could highlight all of these, plug them in, and tell SPSS to figure out which ones matter. So under method, I could say use stepwise regression. What this is going to do is one step at a time include each of those variables and see which one are significant. And it's going to give me a model in the end that tells me which variables matter. I think everything is still correct. Yeah, we're all good here. Yeah, good. All the stuff is there from last time. Okay, great. And I'm just going to say okay so we can see what that looks like. And what you'll get if you run that stepwise regression, you'll see your coefficients for the model that mattered. It was only baseline scores. That's all that wound up in my model. And all the rest were kicked out. They didn't matter. Well, I'm not using regression to try to predict follow-up scores. I'm really using it to control for some variables I don't care about. So I want to force SPSS to include these variables. So I won't run stepwise. Let me clear that regression analysis out of the way. And I'll go back to analyze regression linear. And let's run this the way that I actually would. So I know that I got a lot of variables here and I doubt that they matter. So what I'm going to do is put in my baseline scores. I know those do because I'm looking for the change score. So I must include baseline, and I care about the difference between my control and intervention groups. That's the whole reason that we did this study here. So this is the model that I really care about. This is my most basic model. I can click next over here and specify a different model. So I'll put my baseline and group again, and maybe I think, hey, you know, some subject characteristics maybe matter. Let's put age, sex, and BMI in there. Right? We get like a middle of the road model. I don't have everything in there yet. I got my middle of the road model. Let's see what this is going to look like. So here now you can see we've got our coefficients that are included in the model. Right? Some of these are excluded from model 1 because I didn't put them there. SPSS didn't do it. It's because I didn't specify it. We don't actually care about this excluded variables table. We care about this coefficients table. Right? And what we're seeing is, hey, baseline scores matter, no matter how many other variables you put in, whether it's just group or in the second model, a little more elaborate. Baseline scores still matter. We're not seeing a significant effect and significant difference between groups, right? Because 0 is in the confidence interval, p is greater than 0.05. Okay, so we've seen how we can specify multiple models here. What we have to do before we start specifying models is to ask ourselves which variables are okay to include. And so I've got a lot of 0s and 1s here, but I'm looking at concussion and I'm seeing, hey, there's really nothing going on here. Actually, is that right? The first one should be a 1. Have I screwed something up here? Oh my goodness, yeah, I didn't scroll all the way up. I'm a moron. Okay, cool. So now that we've just seen how stupid I am, notice there's only one person who has concussion. Well, this is pointless to include in my regression model. I don't have enough people who have and don't have concussion for this to be a variable of interest. So rather than me looking at this and trying to figure it out on my own, I'm going to go to analyze, descriptive statistics, crosstabs. And so here what I can do is across each row, I'm going to look in each group. That's going to be my rows, and the columns are going to be these other dichotomous variables: the pain, the injury, the surgery, the concussion. I don't think I care about specifying anything here. You know what? Throw me a chi-square. I want to see if there's any difference in their counts. I'm going to say okay, because really all I want to look at are these things, these counts. And hey, there's 4 people who have current injury in the control group and 7 who have it in the intervention group. Is this difference statistically significant? No. If we look at the chi-square, P is not less than 0.05. But what I'm really looking for here is to make sure I've got some folks who have current pain. 17 out of my 49 do. 11 have a current injury. So these make sense to include. Previous injury, kind of questionable, right? We don't have a whole lot of people with a previous injury or a previous surgery, and I damn sure can't include concussion. So what I'm going to do now is build a slightly more elaborate model, but I'm not going to include concussion because I know I just don't have the counts for it. I'll leave this stuff here. I'm going to minimize it, but I'll leave it there in case we need to come back to it. Now we're going to go, for the last time, I promise, analyze regression linear. We haven't lost anything. Now I want to specify my next block, again, baseline, group, age, sex, BMI, current pain, injury, previous injury and surgery, all this chunk. This is my full model. And again, I'm not trying to predict anything. I'm using regression to control for differences in age, sex, BMI, all that jazz. So anytime you read a study and they say, we controlled for the effects of smoking and BMI and diabetes status, here's what they did. They just put all those things into their regression model. Okay, let's take a look here and see what's going on. Okay, so the first thing we want to make sure is that our Durbin-Watson statistic over here is between 1 and 3. Okay, great. We have independence of errors. Love it. We want to look for our variance inflation factor. There it is right there, VIF. We're looking for multicollinearity. Are my variables highly correlated with one another, and is that maybe, decreasing the power of my model? I'm looking for anything above 10 here. We're not even close. It's all fine. I'm not worried about multicollinearity. Another way you can look for multicollinearity is to make a correlation matrix. So let's say I was worried about it. Well, I can go back here and we can go to Analyze, Correlate, Bivariate. So let's say I was a little worried. I wanted to make sure that, for example, group and age and BMI, and let's grab these, weren't highly correlated with each other. Ah, well, heck, let's put everything in from the model. I can put all those variables over here that I'm worried about. And if you want, you can put everything, no biggie. Click OK. And now I'm looking to see, do I have any correlation coefficients that are like above 0.8 or 0.9? If we see something pretty close to perfect correlation, we're worried. Usually multicollinearity doesn't matter. But if we take a look, Pearson correlation coefficient, so group, yeah, nothing really going on there. Right, it's obviously correlated with itself, so don't worry about that one. But all these other correlation coefficients are quite small, right? Baseline scores, quite small. None of these matter. Yeah, they might be statistically significant, but do they really matter? Hey, previous injury and surgery, those are kind of well correlated. Okay, whoa, sex and, oh, sorry, my goodness, I was looking at the p-value. Okay, so yeah, that one I might care about. Have I lost myself? There we go. So this 0.697, that would be previous surgery with previous injury. So those, again, we're not close to perfect, so I'm not too worried. And again, I'm not using this model to really predict anything. It's just to control for differences in age, BMI, pain, injury, sex, so that I can give an adjusted between group difference. Okay, not worried about multicollinearity because I'm not seeing perfect correlations here. My variance inflation factors were not above 10, so I am not worried about this. Let's go back up to my regression output here. And now I want to think about, do I have homoscedasticity, right? Do I have equal variance of the residuals across all my predicted values? All right, let's take a look. If we scroll down here, we're looking here at our predicted value, regression. This, I'd say, is best explained by a flat line. There's no reason to think there's a whole bunch of positive or negative values on one side and compared to the other. No, flat line looks the best here. That's exactly what we want to see. I'm not seeing some upward or downward trend. The normality of residuals we can see with these two plots. My histogram, yeah, it's not a perfect bell curve, of course, but it follows it pretty well. And when I look at this PP plot here, my dots are following the line very well. I wouldn't even be worried about these anyway, but hey, everything looks cool to me. So I'm ready to go and start interpreting my output here. So let's go to my coefficients, and here's my three models. The most basic model, model 2 here, takes into account baseline and group, but then patient or some subject characteristics inherent to them. And then this third full model looks at their pain and injury and surgery. Now, in all of these, you'll notice there's only one significant variable, and that's baseline. Group, we can see is maybe kind of close, but not there, so we don't have a difference between our groups. Both groups improved similarly, is what we would conclude here. And we could say, you know, our unadjusted confidence interval would be here from model 1 after adjusting for age, sex, BMI, current pain, blah, 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 blah. We would have this confidence interval. And both of them include 0. So there's no reason to think that one group got any better than the other. Now, we of course have to then ask ourselves, hey, what is a meaningful change? I don't know. If it's something less than about 6 points, well, then I'm worried about statistical power. There might be, let's say it's a 5-point difference. There might be a 5-point change. Okay, well, if that's meaningful, then I'm going to need a bigger sample because I'm telling you that there's no difference, but there might be an important difference. Well, that doesn't make any sense. I don't know what's an actual meaningful change here because I'm not familiar with the outcome, but we get our confidence interval here. We can see there's no difference between how one group changed versus the other, right? And so that confidence interval is going to be very important to report there. We probably wouldn't care at all about reporting any of these other confidence intervals for age, sex, BMI, pain, injury, surgery. These are just background variables that we just want to control for, but that doesn't matter. We'd want to look at our baseline, right? But again, this is just so we can get change scores, right? The only confidence interval we're caring about here in this case, from this analysis, is that of group. That was the whole point of running this regression, is to see is there a difference between how the groups changed over time after we control for all these other variables. So we pull that out and we plug that one in. In other cases, we might actually have multiple predictor variables that we do care about, and if you do, make sure you're reporting their confidence interval, you're reporting their, of course, p-value. The t-value is also useful for some people. Some stats nerds might care about it. But very minimally, we have to report the 95% confidence interval. As far as your model goes, you'll turn to the model summary table, and that tells us things like how much of the variance are we explaining. That's that r squared. Now notice what's happening with the adjusted r squared. Even though the r squared is actually getting a little bit better because we're including more variables, adjusted r squared penalizes us for including more variables. Look, anytime you include another variable, your r squared increases. That's just a fact. And so hopefully what we have is a good reason to include those additional variables. And we really don't here as far as trying to predict. In order to control for them and give this nice adjusted between group difference confidence interval, yes, we need to include them. But should we include them if we really wanted to predict with regression? No. And that's where this significant F change comes in. So model 1, just looking at baseline scores, adjusted r squared 0.622. This is our best model. And let's say we include age, sex, BMI. Is that any more helpful? No. This does not significantly improve our r squared value. It improves it by a whole whopping 0.007. But we've had to include 3 additional variables. So this is not a statistically significant improvement. No need to do it. Same thing with that third model. This doesn't help us at all. Yes, we increased the r squared a little bit, but we had to throw in 4 other variables to do it. So it's not a significant improvement. We'd want to stick with good old model 1. Well, actually, we'd want to go with just baseline whenever we did our stepwise. No reason for the other variables. They don't actually predict anything. They were included, again, just to make sure we controlled for them in our analysis of between group differences. That wraps it up for this video. If you have any questions, make sure you make use of that questions box so I can help you out. Or, of course, email me. All right, have a good time analyzing your data.